It's a great pleasure to have you here. Especially have a talk from you on this topic of scalar field theories, which is right at the intersection of what many people work on, who regularly join this seminar. You, according to my knowledge, were graduated from Bonn, obtaining a doctorate in 2010, and you've held positions at Warwick and currently are holding a professorial position at Bath. Thanks for coming, and the floor is yours.
Okay, thanks. So thanks a lot for the invitation. It's really nice to be in the seminar, and when scrolling through the Zoom link, I'm very happy to see so many familiar faces here. So it's really a pleasure to be here. So I was thinking a bit about what to do for this talk, and so I came up with the idea of, in the end, I'm just going to give a bit of an overview of a number of results that that I've been working on in the last few years. And so all of this is going to be concerned with phi to the fourth theory in one way or another. And I'm just going to start the talk by just reminding, just to set basically the notation and to fix what I'm talking about. So, but I'm going to, in one way or another, always going to speak about this phi to the fourth theory in continuum, which is formally given by this expression. You have this if you want to, can view it as a Gibbs measure, then you would have this Hamiltonian here, and then you have this formally infinite dimensional Lebesgue measure here in the underground, in the background. And of course, the way this has to be interpreted is that you take it to the lattice discretization. So here I have just discretized my lattice, as you can see in the picture, and I take a suitable approximation of this expression up here, and then I pass to this ultraviolet limit as epsilon goes to 0. And of course, as most of you will be aware of, that there's this issue of renormalization, that one has to add extra counter terms in order to make this object converge to a non-trivial object, a non-trivial limit. Also, just to make clear from the beginning, so for me throughout this talk, D is almost always going to be equal to 3. Well, with some exceptions, but except most. So, perhaps just as a reminder that this is, of course, an extremely classical topic that people have been working on at least since the 60s and 70s. And there was this huge body of work in the program of constructive field theory that I think many of the other members of the audience know much more. Have been involved in actively for quite a long time and know much more possibly about than I do. So I just want to, I'm certainly not trying to give an overview over the literature, because that would take a long time, but just to say that, there's this classical problem that to even make sense of this measure and to check that it satisfies this set of Osterwalder-Schrader axioms, which is sort of the minimal set of properties that it should have to be a sensible, to give rise to a sensible quantum field theory. And so this has been resolved famously in the three-dimensional case. There's in particular these prominent works by Glim and Jaffe from the 70s, and then many works that have followed since then. And in 4 dimensions and higher, it's known to fail. And this was already understood in the 80s. And there's this work by Ising and Fröhlich. And the 4-dimensional triviality result was, I think, conjectured for a long time, but has only been fully resolved relatively recently. And I actually think that this has been the topic of the seminar not so long ago. So the angle through which I want to go at this problem in this talk is this as a stochastic analysis. So as many of you I'm sure are aware of, there's been a lot of activity over the last couple of years to approach this classical object with I would say new point of view. So to view it as an object really of stochastic analysis and see what we can learn about it using this different point of view. And I have on this slide and in the next slide I have 2 kind of complementary situations how you can make stochastic analysis enter the field, and this one is possibly the one that more of you will have seen. So as I recall here on the top just this fact from finite dimensional stochastic analysis. So if you have some measure on RD, and it has this form. It has to have this Gibbs form, e to the minus with some potential v. Then you can immediately construct a reversible stochastic process for it by just writing down the stochastic differential equation. So you take this this gradient flow here, so the potential, you go down along the potential, but then this is perturbed with the with the noise. Okay, so it's important. I mean, here I just wrote gradients, so it's important in order to get the reversibility of this measure that the gradient with respect to which one defines this gradient here is kind of the same that gives you the quadratic the spatial covariance of the covariance of this Brownian motion. And so I mean, this is of course very well known, and actually the I mean, variance of this factor, of course, used very prominently if you want to do simulations, or if you want to actually draw samples from such a measure on a computer. So there are many Markov chain Monte Carlo algorithms or something that are based on running such Langevin dynamic. And so what one can just do is write down the formal infinite dimensional analog of that, and then you end up with such a reaction diffusion equation. So here you take this, if you want, the L2 gradient of this this energy or action functional that you have here, and that just gives you here this this Laplacian and this cubic nonlinearity. And then again, you have to take the canonical Brownian motion here that that corresponds to the scalar product that defines the gradient, and so you have to take space-time white noise here in order to get the correct measure. And so SPDEs of this type have been studied a lot over the last years, and I mean very prominently, of course, Martin Heyer's work on regularity structures. This SPDE that I wrote here was one of the very first examples that was treated within this framework of regularity structures, and then there are also, of course, these works by Massimiliano Gubinelli and collaborators on paracontrolled distributions that also looked at this equation. Another point of view that I want to actually advertise a bit in this talk, which I like a lot, to look at these measures using stochastic analysis techniques, is something more recent, which was put forward by Barashkov Gubinelli and has appeared in the Duke Math Journal just last year. And that is a variational representation of the partition function of this measure. So if you look at this, the partition function that I write here, so basically the normalization of this this 5 to the 4 measure with respect to the underlying Gaussian reference. And I mean, okay, but what I mean by that is, of course, you discretize the measure and you see how it diverges as you let the divergence, as you remove the regularization. Then Barashkov and Gubinelli gave actually a very nice, explicit variational representation of this object, and they were able to reproduce, among other things, with that the classical estimates that Glim and Jaffe obtained in their first paper on the ultraviolet stability here, in for me completely mind-boggling simplicity. I mean, I really like that paper. And it really gives you a lot of handle in order to do these kind of calculations. It's a, I think, 25-page paper, and everything is included. It's really very elegant. Let me, also just say that what they do has some relationship to the Polchinski equation that, again, I know many of you are very familiar with. So they, in some sense, solve that. And just as another point, and perhaps to contrast, sorry, I don't want to do that, just to contrast that to these Langevin SPDE that I had showed you on the previous slide. This Langevin dynamic, of course, doesn't see the Z. So in a sense, the stochastic gradient flow, well, you never see the partition function, which is either from your point of view an advantage or a disadvantage. So in the point of numerical, from the point of view of numerical simulations, that may be an advantage that you don't have to calculate it in order to draw samples, because it may be difficult to sample it. But on the other hand, it also doesn't give you any handle on calculating the partition function that you may want to do. So I think both points of view are, depending on your point of view, very, very useful. And there's some common philosophy, I would say, between these different points of view, but both in the singular SPDE and in this variational technique point of view, you have a combination where you use a perturbative analysis, which I think is really very much in the spirit of what happens in a more RG renormalization group type analysis of the thing. And I think, I mean, perhaps the conceptually more difficult part, a different part, is then how you deal with the remainders and how you actually treat the errors. And there you use very different techniques, often used PDE analysis and perhaps from harmonic analysis, depending how you want to call it. So what I want to actually now more specifically present in this talk is actually two classes of results, very, I mean, somewhat different, and that I've been involved in over the last years. So there's the first one is concerned with the parabolic dynamics. So there the question is, how do you use the parabolic dynamics to actually construct samples from the measure, and what kind of estimates can you get? And I mean, this is I mean, based on work mostly that I've done already, I think 2 years ago with my then PhD student Augustin Moinat, and then more follow-up work with AJ Chandra and Augustin Moinat. And then the second class, I mean, second result I want to present here is completely different, and it deals actually only with the well, I mean, it deals with the breakdown of ergodicity in some low temperature regime. So I want to explain to you how you yeah, I mean yeah, I mean, okay, I'll come to that in a minute. And this is based on joint work also with AJ Chandra from Imperial and Trish Gagunaratnam, who was also my PhD student here until last year, and who has now moved on to a postdoc in Geneva with Hugo Dominier-Copin. And perhaps also just saying this right away is that the second, I mean, just to link it to these different perspectives that I had mentioned in the last 2 slides, is that the first one, of course, is very much about parabolic dynamics and uses PDE techniques, whereas the second one is actually it builds technically very heavily on this variational representation, and then a lot of more statistical mechanics reasoning, and it's, I mean, actually very different. And perhaps I can also show a bit like the breadth of kind of things that you can now do with these new statistical, these new stochastic analysis techniques. So let's start perhaps with this 5-4 equation, and this was actually one of the immediate problems that people were aware of when Martin put forward his work. Now, I mean, already 8 years ago or so, was if you read these first groundbreaking works on SPDEs here, so Martin's work on regularity structures, or this Kataychuk that was actually done more or less at the same time as Martin's, or a little bit later, but it appeared much later, or also Antikopian's work on using RG on this techniques. They all they were all short time solution theories. So they were, in a sense, they were all perturbative analysis around the basically the linear equation, and the small parameter, in a sense, is the small time. So all of these results gave you a well-posedness stability theory, but only for a small time that is even random. So the time, you couldn't put a small parameter in front of the nonlinearity, the deterministic, but you actually could only solve it up to a finite time. And that is, I mean, in a sense, not really enough for what one wants to do, because if you think of one of the main motivations why one would want to run such a Langevin dynamic is, of course, to let it run for a long time and get samples from the invariant measure on a computer, for example. And then a short time existence result is really not enough. And so, I mean, then this was, I mean, then picked up, and so the first group, I think, there was Jean-Christophe and me who addressed this problem, and then there were follow-up works by Gubinelli and Hoffmanova, and I want to just actually present these kind of, for me now, state-of-the-art estimates with Augustin and AJ, which I think really, I mean, I think they're really quite strong, and I want to just well explain them to you. And so the result that we had in this paper, which we wrote like 2 years ago, was what was this? So we what you do is you start with this this equation that I had written down before, and again, I'm always going to be a bit quick with the counter terms. So everything, of course, has to be renormalized, and it's sort of the same kind of renormalization that you would have to do in the equilibrium case, or for the measure. But I'm going to brush that a bit under the rug and kind of talk about it as little as possible. But it has to be done, and it works. So, but I want to state this theorem as this. It's really a PDE type estimate, in a sense, as you have just a solution of this equation, and it solves the it solves the equation on the space-time set. So you have here this time set and a ball in space if you want. And so what the statement says is now we're going to, is everything? Was there a question? Perhaps not. Okay. So what I'm saying is that you can now what you now do is you do a kind of, if you want, a first step of a perturbative expansion where you just subtract the solution of the linear equation of that. So you write your solution as the solution of the linear problem plus a remainder. And then, so I mean, here this is yes, it's the linear equation. So if you want, this is the Gaussian free field. And then the statement is then this V actually satisfies this a priori bound, where you so you take a look at this the ad infinity norm of this V. So I've drawn a picture here. So here's the big domain where the equation holds, and then here the red area is where I have an estimate. So you give yourself distance r from the boundary, and you have to do it in a parabolic way. So r squared in time and r in space. And so then you can bound the L infinity norm on that set by up to a constant by 1 over r and some more tau. So I'll explain a little bit what that is in a minute. But these are more terms in the perturbative in the perturbative expansion. So the way this theorem works is it's a pure PDE theorem, but it uses as input basically that you have a local perturbative expansion up to a certain degree. So if you want, you've performed your RG analysis up to a certain perturbative level, a fixed perturbative level, and then you can bound the remainder and get this very strong a priori bound. And let me also stress that there's no small parameter here in front of this phi cube term. So you can put 1 or 10. I mean, right? I mean, it doesn't matter. There is no smallness anymore, anywhere, and it really just uses here uses very strongly this cubic damping term. So let me perhaps just discuss a couple of features of this estimate, which is, so these trees, I had already told you, these are terms in a stochastic expansion. So, I mean, these are all super renormalizable theories. So you don't only have to renormalize a finite number of perturbative terms in the perturbative expansion. And these are, I think, actually all given in this list here. And I mean, these are all explicit polynomial in this underlying Gaussian noise, and they can be controlled. I think that I mean, borrowing the word from Felix Otto, he called this offline. And I would perhaps, I mean, or other one could choose, this is a perturbative analysis. So you can really split very well if you want an estimate or covariances or so on these polynomials of the Gaussian, and then you can plug it into your PDE machinery and you get this nice estimate. Let me perhaps also stress another point about this result that I mean, this is an estimate that does not need, it does not even see at all what happens at the boundary of the set. Okay, so you assume that this PDE holds on some cylinder, but you make no assumptions whatsoever what it does on the boundary of that cylinder or outside of the cylinder. If the function is defined or not, doesn't matter. And the point is here that you get an estimate which, I mean, which is sort of uniform over whatever happens outside of the cylinder. And of course, this is very, very useful if you want to get kind of to large times, or if you want to go to infinite volumes or so. You can just place your cylinder where you observe wherever you want. And I mean, just kind of to kind of put this into context, I think this is very. I think it's good to compare this to this. Just the simple situation when you solve an ODE and you have a superlinear damping term, like for example this x cubed. Then of course, I mean, okay, in this example here, you can just write down the solution. It's just that, and of course you can always if you only know that the equation holds, you can always bound it actually uniformly over all choices of initial datum with here, right? So you have sort of one solution which is above everything, which starts at plus infinity. And the estimate that we have here is, if you want, the SPDE version of this simple ODE coming from down from infinity trick. Okay, so that you have building on this cubic damping that you have estimates that are yeah, I mean, so that really builds so strongly on this cubic nonlinearity that you don't need to know anything about boundary values. Another point that I kind of like about these estimates, and that is actually quite useful if you want to apply it to studying the fields in equilibrium, is that you actually get very good stochastic integrability. So I told you that these I mean, you have in your estimate on the right hand side, you always have these stochastic polynomials in the Gaussian noise, and then you have here an exponent. And this exponent actually, I mean, it's actually explicit, and I think it's optimal. So you have this n tau number that appears here is always the degree of the Gaussian polynomial. So for example, I mean, right? I mean, I just mean if it's quadratic in the Gaussian or cubic in the Gaussian or quartic, and then this n tau is just 4 if it's quartic. Okay. So for example, here in this case where you have a square of the solution of the linear equation, then this would just be 2, this number. And so, I mean, all of these numbers, all of these terms are now polynomials in the Gaussian, and in the estimate they appear here with 1 over the degree of I mean, the homogeneity in the Gaussian noise. So if one just uses some, well, Gaussian integrability of these terms, then actually all of these terms behave exactly the same according to because of this 1 over n tau, and you get actually very nice, strong stochastic integrability from that. So so you get that so this v, the remainder, but then hence also the solution has these nice strong stretched exponential tails. So for any small epsilon, you can bound the L infinity norm of this remainder v, well, the expectation of this, or I mean the thing. So you get very, I mean, you get nice stretched exponential tails even in this strong topology, in this L infinity topology. Okay. I mean, perhaps just going one step further in this thing. So these are stretched exponential tails, but I mean, this is, I mean, in principle, I mean, we were very happy when we found this, and I actually think that this is an optimal estimate here in this topology, but it is actually not sufficient for if one wants to check the OS axioms for this one. So because in these axioms, you would actually want the epsilon to be 0 and to allow for any number in front, right? So I mean, one of the axioms would be that you have all exponential moments, that you have all exponential moments, and so that you don't get with our method. But there's actually a very recent, very nice work by Martin and his PhD student Steele, and they tweaked our method and actually proved that if you look in a weaker topology, so I mean, here we have the L infinity topology norm of the remainder, which is strong, but they looked only at the field, the original phi field, tested with some smooth, nice, compactly supported test function, and then they could prove actually this optimal e to this linear observable to the 4 integrability, which of course corresponds exactly to this good e to the minus 454 in the measure, right? I mean, this is the best you can hope for. And I mean, this is a very cute argument. I really advertised this paper. It's very nice. It's really a cute tweak because it basically uses our estimates. It just applies them to a slightly different equation, which so instead of getting the optimal integrability for the solution itself, they actually just tweak the equation and then use the same techniques. But then as a price to pay, you only get this in equilibrium. Oh, sorry, you get the result only in equilibrium. You don't get it for the solution of the SPDE. But then I mean, that's what you want to solve anyway. Let me perhaps also just go one step further in the analysis. So I mean, following this, we actually went further in this PDE analysis, and I mean, if you look at the way the analysis works, which I'm going to just sketch very, very roughly on the next slide, one notices that the dimension of the underlying noise actually only enters very implicitly through the regularity assumption on the noise xi. So the space-time white noise is measured in the right way, has regularity minus 5/2 in 3 dimensions, and this 5/2 is I mean, it depends on the dimension. Every extra dimension costs you minus 1/2 a degree of regularity. And so what we did in this project here is we just said, well, I mean, let's just play this a bit further, and let's just make the noise more irregular and just pretend that we can emulate fractional dimensions with that. And so, I mean, I've shown this here in this analysis. So, I mean, you have dimension the dimension enters the analysis only here, as I said, through this regularity minus t minus 2 minus d over 2 of the noise. So then the critical value here would be 4 dimensions. So it's so what we did in this here is we just said, well, let's just emulate fractional dimensions a little bit better than 4, because clearly things will not work in 4 dimensions anymore. By working with a noise term which has regularity just a little bit better than -3, which would correspond to the 4-dimensional situation. So I mean, this could in practice be implemented, for example, by just taking a real 4-dimensional space-time white noise and making it a little bit nicer by applying a small regularization, say some small negative power of the Laplacian to it. And then this makes actually the analysis much harder. So it requires then local expansions of arbitrary order. And yeah, I mean, so we were kind of happy that our method is stable enough to hold for that case. But perhaps, let me also just admit immediately that perhaps for this audience that this is possibly not the correct way that one would want to emulate fractional dimensions from the physics point of view, because this is kind of the natural PDE extension of our method. But you would not expect it to give rise to a reflection positive measure. So it's in a sense the wrong way of emulating fractional dimensions. There's actually a different way of emulating fractional, pi4 to the theory in fractional dimensions. There's this work by Bridges, Mitter, and Scopola, and what they do is instead of kind of playing with the regularity of the noise, is they actually put fractional powers of a Laplacian, and that's something we're actually kind of thinking about to see if our analysis still works, and I'm kind of confident, but yeah, that's that. I have one slide. I have not so much proof in this talk, but I wanted to have one slide to just give you a little bit of a flavor of how all of this actually works, and just to show these are really analysis techniques. So what one does is I've kind of summarized the proof in four steps, and I hope you can read what I wrote here. I'm more or less convinced. So what you do in the first step is actually relatively simple. Is you just take the equation for this remainder v and you regularize at scale t. And what I mean by this regularizing is just you convolve it with your favorite kernel, say a Gaussian with variance, with a Gaussian with variance t or something, okay? With a standard deviation t, say. So what you will get here is, in a sense, of course, here what you get is that the heat operator, of course, commutes with convolution with a nice kernel. And then you want to write here the cubic of this convolved quantity, right? Because this is you want to have a closed expression, and you want to use the fact that you have a strong damping here, and you want to use the cubic damping to help you. But of course, cubing and convolving don't commute at all. So you just put in this commutator term here, which just makes up for that error, and then you regularize all your other terms. So this is now, one has now succeeded at this stage in getting this nice operator in front. But of course, the price to pay is that this equation is not closed in itself at all. And so now what one does is one puts in two different ingredients, completely different. One is now just using, we look at this equation, we use the fact that that we have the strong cubic damping here, and we use some version of the maximum principle, which tells us that we have the bound that we want. So for the smooth quantity, we have this coming down from infinity term here. But what we have to control, of course, are all these error terms here. So we have here all of this, well, including this here. All of this just is still, it's theirs. It has to be controlled. Let me perhaps also stress these exponents 1/3 that you have here, which are extremely important in the analysis. And they really, this 3 is the same as that 3 here. It really corresponds to, and this is where we use the nonlinear damping. If we didn't have this 1/3 here, we would be, nothing would work. So that's one thing, but now of course this is still not closed. And now this is the bit where we actually basically use this whole theory of regularity structures, which allows us to, which allows to control products like that. And the way we had to rewrite this a little bit, well, actually a lot, the way Martin had written it down, but the way we use this is as an interior regularity estimate. So I mean, it's typical for a solution of a parabolic problem that you can control higher regularity norms on some set by lower regularity norms on a bigger set plus the right-hand side. And that's the kind of estimate that that's the way we rewrote this analysis that Martin had done. Let me perhaps also just here give credit that this is very high. This part is certainly very highly influenced by what I learned from Felix Otto on our work on some other problem. So it's a really completely different analysis here. I mean, here in this step, you really use very strongly your cubic damping, and it's a kind of you see the smooth system, and then here you go to smaller and smaller scales and basically bound a high regularity norm by a low regularity norm. And then once you have control on this high regularity norm, then it allows you to control all of this stuff and you get a closed system. So that's then the conclusion. You use the step 3 to bound these 1, 2, 3, and then you get an estimate that you can iterate and you can conclude. Okay. I mean, okay, this was of course now very quick. So this ended. The point of this slide is only to give a really vague flavor of how this works, and also perhaps to contrast it to the second topic that I'm going to get to now, which is really quite different. So the second topic we look at. Perhaps I just make a quick pause for 5 seconds. Is there anybody who has a question? I think because this is a good point. Okay, so then let's just continue. So the second topic I want to talk about is now this question of phase transition for these 5 to the 4 fields, and I'm going to look at a slightly different version of the measure. So instead of just this quartic nonlinearity, I'm going to put in here this sort of double well form of my potential. So I have I mean, okay, here's the sketch, right? I mean, this potential here has now this double well form. And with minima at plus and minus square root of beta, and the potential barrier between the wells is of height beta. And now what I'm going to look at for this part of the talk is a situation where beta is very large. And the idea is, of course, that the intuition here is that transitions from, I mean, between these values here should cost us a lot of energy, and should be very expensive in terms of this this gradient Dirichlet energy, Dirichlet and integral form. And I mean, I would also like to argue that for large beta, this actually looks very much like a low temperature Ising model. And okay, I mean, here on the left, I've just recalled the definition of the Ising model, which I'm pretty confident that almost all of you will know. So I mean, the Ising model is, of course, as you all know, a spin model, where in a lattice every spin just takes the values plus or minus 1. And I mean, okay, for us, we should perhaps now think of plus or minus square root of beta. And then you have this interaction, this interaction between neighboring sites, which essentially just measures. I mean, you pay a price for how different they are. And so when I think it's just, I mean, just here to bring home this message that our measure is actually very similar to that. So we basically just replace this plus minus delta 1 Dirac reference measure, which is underlying here, by this thing with a double well, which I mean still is concentrated now around plus minus square root of beta. And then this interaction term is sort of replaced by this, or then this would be on a discrete lattice, and then continuum would be replaced by this, right? And of course the cost between transitions will be higher the higher the beta is. And okay, I mean, here this is again just a reminder for something that I am sure this kind of pictures most of you will have seen for the Ising model, that you know that depending on which value this temperature beta has, the behavior is very different. So on the left you have here the low temperature situation where basically your field is constant, and in particular if you look at the spin on one side of the box, of course it interacts, it still sees very strongly, it has a very strong likelihood of being the same as the spin on the other side. And then you have here this would correspond to the critical value of beta, where where this behavior changes. And then in the high temperature regime, where the spin here really doesn't care very much anymore about what happens here. And so what we wanted to capture is the is sort of this large beta, so low temperature phase, which corresponds to this picture on the left. And I mean, before I go into our result, let me perhaps not hide the fact that this is of course classical. I mean, people have been looking at this a long time. I have been looking at this a long time ago, and there's in particular this very, I mean, famous paper by Glim, Jaffe, and Spencer, also from the 70s, who observed exactly this long-range order phenomenon for large beta in the two-dimensional case. So this was strictly for the two-dimensional case. So their result is this: they look at a box, two-dimensional box of size 1, and then for such a box you look at you define the average. I mean, this is just a notation. So here I just define this phi of the box is by definition just the average of this field over this box. And then what they proved is this long-range order that I've kind of showed you on this cartoon on the previous slide. So what they proved is that if you look at the covariance between here's the covariance of the indicator that this is positive and that this is. I mean, okay, wait. Let me say it differently. So the probability that if this is positive, then this will also want to be positive, at least even if the red box is very, very far away from the blue box. And they proved this uniformly in the distance between the red and the blue box. So that's what this estimate here, what this estimate here expresses. Let me perhaps also say right away. So this analysis at the time was really limited to the two-dimensional situation. And for those who know, this is based in spirit very close on this classical Payal's argument that was first used to even prove the existence of phase transition from the Ising model. There is also, let me also say that in three-dimensional, there's also a result that proved long-range order, but that is very different in spirit. So there's these are these infrared bounds and uses very strongly reflection positivity, and it's a very different argument. And so what we proved now with AJ and Trish, we went back to the situation in the three-dimensional case, and what we proved is this. So we look at this on a very large torus. So you should think of large n. So this is a torus, large torus of size n. And we look at this nu is the measure that is this double well 5-4 field, 5 to the 4 field that we had that I had shown you a couple of slides ago. And then what we prove is that if you look at the average spin over this whole torus, so if you want the mean magnetization or so, then the probability that this is less than half square root of beta, then this is exponentially small. So you see my cartoon down here again. So you have this, there's this double well that you have underlying, and it has this minima as plus minus square root of beta. And what we what we showed is that I mean, if you look at this forbidden region here in the middle that I've sketched in green, then your mean magnetization over large boxes really doesn't want to be there. And I mean, of course, let me also just perhaps say right away, this factor half could of course be replaced by anything that's less than 1. It's just half is a convenient number, but I could also have written 0.9. Okay. So that's this estimate. Let me perhaps also just say right away that this is, I mean, at least in terms of the n dependence, this is the correct order. So you have surface order bounds. You have so I mean, if you want, let me just rewrite it without the log. So it just means that the probability of this event kind of behaves like x to the minus n squared times something, right? So it decays like e to the minus n squared. And this n squared factor is of course exactly what you would expect if you have this picture in your mind that how can you actually achieve such a configuration which has spin close to 0? Well, I mean, the easiest way one could imagine would be if you have one big blob in the middle where your spin is plus beta square root of beta, and then you have another kind of area outside. I mean, this is a torus, right? You see my picture, it's a torus. So then outside you would have some other region of roughly the same size where you have.
You will have a strip.
Sorry?
You will have a strip, not a bubble.
So I didn't understand still. Sorry, Roman.
You will have a stripe. It's torus.
Yes.
So
oh
you
yeah,
will
that's
not
true.
have a bubble like that. You will have one half. It's a stripe, you know, through your.
You're right. Sorry, but still, there you will have order n squared. You're right. Sorry, actually, the picture is not good. I mean, I'm right. You're right.
You will have a stripe, you know, somehow.
So the picture should perhaps be better like that.
Yeah. Well, with two lines, you have to. It's on torus, so you have two lines that divide it.
This is the second line.
Yeah.
Okay. Yeah. Sorry, the picture is not good. But I mean, either way, by an isoparametric inequality, you would have an interface between these two areas of at least of order n squared, and that is exactly the n squared that you have here. Okay. Let me perhaps also, this was our starting point actually in this project, that why we were originally interested in this was we came sort of from the dynamics, and we had originally hoped that we could get really an SPDE dynamic argument to prove that the SPDE doesn't equilibrate very fast in this low temperature regime, and then hence we would conclude something about this phase transition. But now it turns out it was actually easier for us to look at the measure and then conclude something about the SPDE from that. So what you get really for free from this estimate is this this breakdown of ergodicity by, I mean, so if you just call lambda the spectral gap of this dynamics, so just which measures the one way of measuring the equilibration rate of this phi to the 4 dynamics, then you get immediately that it decays sort of in the same way as this probability before, and the proof is really immediate. You just plug the right test function in your Dirichlet form, and the test function is basically one that is kind of -1 on one, -1 on the kind of space where your mean magnetization is a little bit below 0, and then +1 where your magnetization is a little bit above 0. Then you see the gradient sort of all lives here, but then this event has basically no probability. So that's how you get this. This is really immediate. Yes. So do I want to say more about this? Perhaps not. Yeah. So I have actually 2 slides there where I want to have a little bit of a flavor of proof of how we do this. So the method of proof, it's now very different. I mean, there's not so much PDE here. Is very much inspired by this Glim-Jaffe-Spencer analysis. So it's to compare our continuum spin system to a lattice spin system. And so again, we look at these blocks. So this is just a notational thing. And well, actually, sorry, my block is 2-dimensional. It would really be a 3-dimensional block. But I mean, the picture is 2-dimensional, but you should imagine a third one here. And we call such a block, say, plus valued or minus valued if the average is close to this either plus or minus curl of beta, as suggested by this picture with a double well. And then we make a relatively restrictive assumption. We say that we call a block plus good if it's plus valued, so if it's close to the square root of beta, and all of its neighbors in such a star neighborhood are still neighbors. So if you go to my picture here, so this red, say this would be a plus valued spin, say, and then you would impose that and all of its neighbors are also plus to be plus good. And then what we prove is actually such an estimate that we call Piers type estimate, where you prove that you fix yourself an arbitrary collection of boxes, and then you prove that the probability that all of these boxes are bad. So I mean, you remember we had this relatively strict condition of what it means to be good. So bad is everything that's not good. And so we prove that the probability for such a collection of boxes to be bad is very small, and in particular it decays here exponentially in the size of the collection. So it's an extensive estimate. Yeah, so that's what we proved. And let me perhaps also just on the second bit give you a little bit of an idea how one can do this. And this is still very strongly inspired, at least what I present here on this slide, by what happens in Glimm, Jaffe, and Spencer's classical analysis. Is that you introduce these functionals here that if you want punish the field if it doesn't behave the way it should. So you have these Q1 and Q2 functionals that punish that sort of are large here. Okay, together that either one of them will be large if your field itself is not close to the square root of beta, and then this Q3 punishes if two blocks have perhaps are too far away. So you should really think of this one being this one being big is unlikely because of the potential, and this one being big is unlikely because of the Dirichlet energy between the thing. And so then what we prove is, that's the key technical, one of the key technical estimates of the whole paper is this bound, this moment bound that this exponential moment bound for these QIs. So we fix an arbitrary collection of these QIs and basically take exponential moments of them, and then we get this kind of extensive estimate, this kind of extensive behavior in the size of the BI. And perhaps, it's important to really contrast this a bit to what was done in the 70s, so that this estimate, or an estimate very much of the spirit in the two-dimensional case, was also present, and in that sense we're not being very original, and that was also present in the classical analysis by Glimm, Jaffe, and Spencer. But I think, I think it was not completely clear how one would get bound estimates, how one would get something like that in the more complicated three-dimensional situation with these much more singular fields and where expectations are much more difficult to estimate. So in the two-dimensional case, you could here use a relatively soft technique, this Nelson trick that works, and getting estimates like that using RG or phase field bounds was seem okay, I'm speculating a bit, but that seems at least to me seems to be much harder. And so what makes this now go for us is really this Barashkov-Gubinelli variational method, which is like this really very strong, powerful, very powerful method to really do calculations of this type.
Question?
Yes, please.
Do you make any use of reflection positivity and say chessboard inequality?
Yes. Yes, and we do it in the same way that Glimm, Jaffe, and Spencer did already in their paper. So the estimate that we do we get this extensive estimate by proving it for the whole for where we take the collection of all boxes and then use chessboard estimates. Actually, this is something that thanks for the question. This is something that when we were working on this, we were thinking a lot if we could avoid this, if we could give a direct proof, and if we could kind of get a localization into this argument with Barashkov-Gubinelli, and at the time we didn't manage. I think it's still very interesting to see if it can be done, but we didn't manage in this time.
So can I still ask in this direction? So you are using your method only for this disseminated disorder somehow, so to say. After doing reflection positivity, you have this disseminated thing periodic.
What does disseminated mean in this context?
And this is what you estimate, yeah?
We want to estimate basically. We want to estimate these exponential moments of these QI functionals. And we need it on collections of boxes which are which can be relatively arbitrary, but we prove it a priori only where the collection of boxes is just the whole torus, and then we use chessboard estimates, as you know actually better than me.
So first you use chessboard estimate, and then you estimate the final thing.
Yeah.
By your method. Yeah.
Yeah. Okay, so now I'm a bit of I think I have to ask the audience what I should do, because how should I do time-wise. So I can now say this is what you wanted to know, or I could explain this Barashkov-Gubinelli method. So I have either a conclusion or 3 or 4 more slides on the Barashkov-Gubinelli method.
So I think you have about 10 minutes.
So then I can do the Barashov-Gubinelli method, and I can do this first. So I skip this thank you and the thing, and I go to Barashov-Gubinelli. That's excellent.
Already thanked us, so let's taking as having already been thanked. So.
Okay, good. So then that's great. Then I have actually still a few minutes, and because I really like this method, and I like to explain actually how it works. And so it is based very much on this Boer-Dupuy variational representation for expectations of Brownian motions, actually. So this is a theorem due to Boer and Dupuy from the 90s, which says this. So if you have a standard RD valued Brownian motion, and you have some functional that depends, I mean, let's just say for the sake of simplicity that is only defined on interval 0, 1. And then you have a functional that depends possibly on the whole trajectory of the Brownian motion, okay? And so, okay, say bounded measurable, I mean, okay, the assumption you like. And then the statement is then you can calculate this expectation here. And you want to calculate this exponential moment of your Brownian motion, and you can give this variational representation. And sort of the nice thing about this variational representation is, of course, you have moved the exp out, right? I mean, before you had to take an exponential expectation and take the log, as you typically do. And now on the right-hand side, you don't have that anymore. You have only the functional itself. But of course, you have to pay a price. And the price that you have to pay are these adapted bounded shifts. So you don't evaluate exactly at the Brownian motion, but at a shifted version of the Brownian motion. And you have to pay a price here that that's sort of the more you shift, the more you have to pay a price. So you can balance between making, I mean, if you kind of take a very suitable V, then perhaps you can make it a bit smaller here. But what you have to do, of course, the bigger the V, the bigger your price that you have to pay. So you don't want to use too much of this V. And okay, I mean, let me also just say that this is actually not a surprising fact. I mean, if you just at first glance, this is not very surprising at all. This is really a variant of this Gibbs variational principle that just tells you that you can calculate these exponential expectations of pretty much any measure. And what you have to do on the right-hand side, you take, again, I mean, now you calculate expectations without the exp and the log. That's nice, but you have to take expectation under an equivalent measure Q, and you have to pay the price as relative entropy, right? I mean, that's well known. But the nice thing now in the specific situation where you have Brownian motion and Wiener measure is that due to Gersanoff theorem, we have a very, very good handle on how equivalent measures to Wiener measure actually look. It's a very rigid setup. You basically know that every measure that is, well, you know that every measure that's equivalent to the law of a Brownian motion is just a shift of a Brownian motion. And that's what this formula essentially captures. So, I mean, if you want to break it down to that, why this is useful is it allows us to use Gibbs variational principle, but we have very, very explicit handle on which equivalent measures actually exist. Okay. So now, how is this useful? Because where's the Brownian motion? Of course, I mean, there's a priori we have, of course, a Gaussian measure with which effectively we want to take the expectation, but there's no time dependence. And what Barashov and Gubinelli said is, well, I mean, we don't have time. Let's just put time there. Let's just put it there. Okay. I mean, let's put an extra time variable. And so actually what I've got on the slide here is a bit of a cartoon, and I'm going to stress this flexibility here a little bit more in a minute, but let me just show you sort of the cartoon version of doing it. Well, you can always, you have any Gaussian field, you write it down in an orthogonal theory. So here you can just write down this and this is basically just the Fourier series expansion of the Gaussian free field. And if you put just the standard Gaussian here, then you get the Gaussian free field. So, I mean, how do you introduce a time? Well, let's just replace the standard normal complex valued by a Brownian motion at time 1 and have this extra parameter t, okay? I mean, voila, we've introduced an extra parameter t. And so there's this Brownian motion. Let me make 2 remarks on that, which I kind of find conceptually important. I mean, one of them is, I think this is really a very nice thing by kind of saying that you introduce the randomness sort of peu à peu. You kind of, instead of having just a single source of randomness, you really have sort of you review this source of randomness as a kind of an accumulation of a continuum of randomness that is integrated up. And that's, yeah, I mean, that for me sort of also uses the fact that normal variables, normal variables are actually infinitely divisible, and sort of builds very much on that structure. Perhaps the more important remark on this for this audience is that actually there's a lot of flexibility here. So you don't need to do this kind of naive definition where you kind of introduce all the Brownian motion uniformly over all scales, and that's indeed actually not what Barushkov and Gubinelli do. But you can actually just use this time parameter as a scale parameter, and that's this link to the Polchinski equation that I was alluding to already at the beginning. So that's also how they actually presented in their paper, is that you can, I mean, the only important bit is that your Brownian motion at some final time has the distribution that you want, and it does not matter really how you got there. So so what they actually do is they say, well, on the interval Z, on the first little bit of time, you kind of take the very high frequencies, and then you kind of zoom over the frequencies. And so in this way, it's really close, I think, close in spirit to what happens in renormalization group analysis. And sort of then once you're there, then you just plug it into this variational representation. And then for reasonable functionals H, you just use the fact that your Brownian motion at time 1 actually has the correct law. So you can just replace your Gaussian field by this Brownian motion at time 1, plug it into this Boer-Dupuy formula, and then you have here now this functional. And now at this point, one really use actually arguments from the calculus of variations to just prove that you have now kind of good terms here and good terms here, and they should kind of control the bad terms, and you just do a variational analysis. So I think what I perhaps show this, I actually have as an example here, but I'll have to rush here. So this is perhaps more panoramic. So there's, as an example here, I have the proof for ultraviolet stability in the 2-dimensional case. So if you want the Barushkov-Gubinelli version of the Nelson trick, so there you have to bound now you have to bound this in this case of high to the 4. So what you do is, in this variational principle, you have here this phi with this field V, and then you have these extra terms here that you have from the Gaussian covariance, so these entropy terms. And then once you expand this, what you have to do is you have, I mean, this is as expectation 0 anyway, you don't care. And then you have here these good terms here, and then you have a bunch of cross terms from the expansion, and then it really just boils down to a harmonic analysis argument that tells you that you can actually control these cross term by the good terms. Okay? So it's really, you write it down, the formula, and then you do a little bit of relatively soft harmonic analysis, and you're done. Okay. But okay, this was perhaps a bit quicker in the end that I had it. So I'll go back almost to the thank you. So the conclusion is that let me just summarize. So I mean, as all of you will be aware, is that this phi to the 4th theory is, of course, a very classical object of study, and many known results, and I haven't even attempted to summarize them. But I would like to just kind of say that over the last 10 years, there's a bunch of new techniques from stochastic analysis that have been used to approach this from a different angles, and in particular, then this regularity structure and paracontrolled distribution point of view. But I also really like to put this variational representation in this list. And the specific results that I showed you here are these strong estimates that we get in the parabolic dynamics that actually allow you to really get pretty good explicit handles on samples from the field. And then the second result, which is completely different, where we kind of push this classical Glimm-Jaffe-Spencer analysis to 3 dimensions, well, really building very much on these techniques introduced by Barushkov and Gubinelli. So I'll stop here. So I'll now finally stop at the thank you slide. Thank you.
Thank you, Hendrik. Now you can already also consider yourself thanked. And we go on with questions or more questions.
Maybe one question for this second part of the talk on phase transitions. You discriminated a bit these field configurations with respect to mean values in boxes. At good boxes and bad boxes, page 22 or whatever.
Yeah.
And what determines really, you said these boxes were unit boxes, but there must be somehow an intrinsic scale which determines what is the good size of these boxes, and for 5 to 4 and 3 dimensions. And
yes, but I think our analysis, certainly at now, is not fine enough to capture that. I agree, but we deal with very high beta, and we can be completely brutal. So I agree with the question, but I don't have a good answer.
Thank you.
It is something in terms of this beta?
Yes, but our beta is just large enough, and that beta large enough allows us to take size 1. But it would be very interesting to understand what happens if beta is perhaps just large, but not large enough.
So if I can ask a question, you mentioned, of course, infrared bounds and all this. Now, these are most interesting for multi-component fields. So can you comment on surely there must be something that one can do with the stochastic method there. Has it been done yet? I mean, if you just take any component fields.
Right. So I don't think much has been done first. So then if you go to this PDE point of view, which I suspect is not what you were aiming at, but in the first part of the talk, I have a more confident answer in the first part. In the first part, I am close to sure that it's absolutely no problem to extend it to arbitrary vector value. I mean, of course, what is important is that your potential has this, I mean, that this nonlinearity has this strong damping term. But if you say, for example, make it complex valued and look at a model in a, I mean, like 2-dimensional, and now you have to say 5 to the 4 with absolute value, then I'm close to sure that nothing changes, except that, yeah, I think that really nothing changes. I think you just want to apply the maximum principle to the absolute value of the solution rather than the solution itself. In the second part, of course, you would expect, say, if you do such a thing, I mean, the second thing, of course, depends very strongly on the symmetry group just being, I mean, just you have this +-1 symmetry, right? The analysis.
Yeah, sure. Yeah, that's, I mean, I was actually more asking about the first part. I mean, I think from the method, it seems pretty obvious that you won't be able to use Peierls arguments for continuous symmetry.
Yeah. Yeah, yeah.
Thanks.
But for the first part, yes, I think it's absolutely no problem to use it for vector valued.
Could you offer some comments on where are we with respect to formulating a continuum critical 543 theory?
Oh, I mean, I think what I've presented here doesn't really help you with that. I think it's I mean, all of these regularity structure stuff, also the variational principle, everything relies as of now very strongly on the super normalizability and because, and I mean, it's technically really important in them because it is used. I mean, as I also showed you at the beginning, you make this very strong separation between the perturbative analysis and the analysis of the remainder, which is somewhat different to what is done in RG, where you kind of intertwine them a little bit more from the one step to the other, whereas here you kind of allowed to take a supremum over all scales at one go, and then kind of completely disentangle the probability from the remainder estimates. And I don't think, I mean, that if you look at it in detail, you always lose kind of a kappa of scaling as you do that. So I don't think that this as such would work in criticality. So I think that the honest answer is all of this, I think, works super well for pretty much everything that is not critical, which means where they're super normalizable. I think it's a very interesting question. In the critical case, I do not know if there's really much progress for now.
Thank you.
But perhaps if you ask Martin, he will give you a different answer.
I think the question was about critical temperature rather than critical dimension. If I
Oh, sorry, did I misunderstand
Yes.
the notion of critical?
Oh, yes, yes, critical temperature. Yes,
Oh,
yes.
sorry, I meant critical dimension now. Sorry.
Sorry.
Oh, okay. So no critical temperature, but the answer is the same. We are so far away. I mean, this is very, very far from criticality.
Or alternatively, if you let's see, if you fix the volume, periodic boundary conditions, I guess you constructed the 5-4 field theory with the finite correlation length, right?
Yes, I mean, on the volume, you can construct everything, of course, yeah. Finite
Including volume. The critical, including arbitrary temperature, so to say.
I mean, but for the construction of the measure, the temperature plays no role. There is no small parameter in this whole analysis.
So how far are we from some basic compactness arguments which prove that there exists something corresponding to critical temperature 5-4 field theory?
I think that my understanding is that that exists. I mean, without any estimates for the. I mean, you have a theory for the critical temperature, but no. I mean, you only know by continuity or something that the susceptibility at some point has to diverge, I suppose, but you cannot really say anything about it. That's my understanding.
Thank you.
Yeah, but I mean, these constructions for us, I mean, also these compactness methods that where we have the estimates don't care about temperature really. That's more the first part. That's, I mean, they're uniform over everything.
Any other questions to the speaker? I think we've had already quite a few also during the talk, and I don't want to add a question that suggests much less insight into your talk than the previous one. So at this point, stop and thank you for being here virtually. And Jochen, who's our next speaker? Could you please remind me?
Andras Vasi.
Yes, our next speaker will be Andras Vasi from Stanford on the topic of Feynman propagators and microlocal analysis. I forget, unfortunately, the precise title, which will be announced in due course. Thanks again, everyone, for coming.
And thanks for the invitation. It was very nice. Thank you.
Bye.
Thank you.